Good morning. Hey, everybody. Toby Duncan here. I haven't done a YouTube live stream for ages. I thought I would respond to my subscribers and say I'm sorry that I haven't. And I'm going to be doing a I've got my chat up on the board. We're coming to that now. What I'm actually going to do is I'm going to pause the video. It's just there for my chat. So I can see myself up here, which is terrifying, by the way. Okay, guys, let's crack on. So today is going to be NMR, and I'm going to be doing 3 lessons on NMR over the next couple of days. So this is just an introduction to it. We're going to be focusing on C13, looking at key terminology. You can see my learning objectives in the webinar description, but I'm going to be sharing it with my screen now anyway. So hello. Hi, Roy. I'm going to call you Roy. Hey, Roy, thanks for coming along. Right, we're doing NMR today, Roy, year 13. So I want to do my entire screen. I think that's the right thing, but I want to pick that one. Share. Cool. So, Roy, I can still get you started. I've also got Ping Ping. Hi, Ping Ping. Thanks for coming along. Right, I'm also going to disable my camera because I don't have an additional camera. So I'm going to stop my cam, make that disappear, and then go just a full screen like this. And I'm going to be doing NMR. This is for year 13, A2 chemistry. Right, let's crack on, folks. Okay, so my usual start to my lessons. I've got key learning objectives that I need to do here. So this is Nuclear Magnetic Resonance, Part 1, C13. I've actually got, for those students who are unsure about the key terms associated with this topic, I've got a list of the key terms. I thought I'd include those at the start of the lesson just because I figured you guys can take a screenshot of that, and these are the keywords that you're going to be seeing on exam questions on a regular basis. So it's useful to see how those will appear in my next 3 lessons. I'll probably be tying back to that at various points. My learning objectives today, I'm going to be focusing on understanding how NMR works. Number 2, I need you to be able to identify environments, both equivalent and non-equivalent environments. So we can talk, this is an extension here because we've got non-equivalent, equivalent, non-equivalent, and equivalent environments. Now, I'll be including a little bit of information here on symmetry as well. I'll be doing that. And then I need you to have an understanding of chemical shift. There are loads of exam questions where you're going to be given data in the form of graphs. And having a good understanding of chemical shift means that you're going to be able to look at the data, and rather than completely relying on the data book information, you'll be able to do some of the questions without really actually having to look at it. And there's some real benefit in that. Okay, the last one is I want you to know your key terms for this. Okay, so NMR, where do we start? So NMR is part of what's called machine analysis. So this is just one part of machine analysis. I would love somebody to say something on the chat just to make sure that the chat is still running. I've got so many things going on in my laptop. And it also means that you can check just to see that the live stream is still going and that you can hear me okay. Every now and again, I'll have an issue with the sound. So it'd be good just to get you guys to give me a little bit of a hello. Can you hear me okay? And is the stream okay? Can you see my screen all right? I wonder if I can do that now. Somebody say hi if you're there. Okay, I guess I'll probably just keep going and kind of hope that someone else appears. Okay, so machine analysis. Machine analysis in A2 chemistry. So at A2, machine analysis comes under 3 main brackets. So you tend to pick up mass spec at AS, mass spectroscopy at AS level. However, there is also an A2 extension, which you see later on. And the mass spec extension is to do with fragmentation with major and minor peaks. You also have IR, infrared spec. So this is analyzing bonds in things. This again is AS, but regularly appears at A2 as well. You tend to see an overlap. You'd get mass spec at A2 as well. And the last one is NMR. So we pick up NMR as another machine analysis. Now there are two types of two types of NMR that take place. We have C13, carbon-13 NMR, and we also have proton NMR, sometimes just called hydrogen NMR, but you'll see it in 99% of the questions. They call it proton NMR, and sometimes they even include the symbol of H1 as well. What I will also inform you is that there are other types of NMR out there as well. I've been teaching this for a while, and I've been waiting for questions to appear based around other NMRs, but they never seem to. You also have fluorine-19 MR, and you also have phosphorus-31 as well. That's another common one. Nitrogen-15, I believe, also exists. But those are the other two. You do not need to know these. These are purely extensions. But there is a nice thing to pick out about this. And that's the fact that all of these NMRs rely on one particular structure of the atom. So all NMRs revolve around the concept of having an odd number of nuclei, an odd nucleon number. Yeah, so this one has an odd number of 13, this one has an odd number of 19, 31, and of course 1. What this means is, I've got students standing up, help, I'm live streaming. I've got students pestering me. So with an odd number of nuclei, this means that we can actually see them in this machine. Without it, with an even number of nuclei, you cannot be seen in an NMR machine. So I'll hopefully add a bit more information onto this as we go through the lesson. I still haven't had any more mentions on the chat, so I don't know whether or not anyone can hear me. I don't have a clue whether or not this is functioning properly, but we will continue as if it is. I don't even think I actually have another recording of it, but I'll keep going. So an odd number of nuclei. The two that I'm actually going to be starting with C13 today, and then I'm going to move on to proton in a later session. So how does this work? So I think the first thing it's good to describe here is to have an understanding of how you prepare a sample. This is commonly not really discussed by teachers in lessons. They tend to just jump right into the actual theory of the machine itself. But actually, there's a really reasonable process here. So let's say that we've got a sample. I'm going to take a sample of a solid. And what I'm going to do is I'm going to identify a single particle in the solid. And there's a reason for me doing this. So if I want to do analysis on an organic substance, by the way, just to add this into my notes at this point, NMR is only organic. This is for organic analysis. So we can add that on there. So this is not inorganic. This is only for organic carbon-based molecules. And what we're going to do is we're going to take our solid sample. And the first thing you have to do is you've got to dissolve it. So the first thing I'm going to do is I need to dissolve my sample. And this process is really important because if you didn't dissolve it, the particles that you have would interfere with each other. And you just get garbage results in your NMR. You need to separate out the molecules entirely. It also needs to be relatively dilute, not that that's a question that you ever see. You want to make sure that the molecules are not interacting with each other. So we're going to dilute this in a solvent. And it's nice at this point to mention the solvents that we're going to use. Now, if your inorganic substance with something like, it'd be nice to try and add in a solid here. If you wanted to do something like, I don't know, a good one, benzoic acid, that's quite a nice one. If we were going to analyze benzoic acid, now benzoic acid is a solid at room temperature, and I need to dissolve it in a solution. I'm going to need a solvent that is polar. Because this structure here has a polar ending, I'm going to need to have a polar solvent to do this. Now, there are two common solvents used in NMR. We've got CdCl3, which looks like this. I replace the hydrogen. Now, this, of course, the D comes into one of my key terms, which is this term deuterium. Now, deuterium is a hydrogen atom with an additional, with a neutron. So H1 is just simply a proton and an electron, whereas deuterium is actually 2. So it's still technically hydrogen. You can actually do or H2 and 1. Yeah, but we actually give it its very own symbol. And that symbol is D, standing for deuterium, which is an alternative name for heavy hydrogen. So we actually use the symbol D here for this. Now, the reason why we're doing this is because what we want to make sure that the hydrogen, when we're using this for something like proton NMR, doesn't make an appearance in the data. Now, obviously, the carbon-13 is going to appear. The carbon atom will appear in C13 NMR. However, it's nice just to add a nota bene at this point. Nota bene, CdCl3, and it's nice for me to add in the other one. The other alternative is CCl4, tetrachloromethane. These are our two common solvents. There are the other solvents, by the way, but these are the two most common and ones I'd expect you to learn. Nota bene, CdCl3 and CCl4, both contain hydrogen. Both, I'm going to change my pen thickness a bit too thick. Both contain hydrogen. Contain carbon. This means there will be a peak. Would give rise to peak in NMR graph or data, NMR graph. However, its chemical shift is well known, so it's removed from the data. However, chemical shift well known. Chemical shift is known, so removed from graph. So computer removes. So it does, but the computer removes it. So you don't see it. It's quite nice. I've never seen an exam question on that. What you do get is exam questions on the D. That one does appear. Now, since this is a polar benzoic acid, since it's polar, I'm going to be using, to match the polarity, this is going to be a better, because this is a polar solvent, whereas this one is a non-polar solvent. So you pick the solvent based on what you're trying to dissolve and what you're trying to analyze. So in this case, it's polar, so we're going to be switching to CdCl3. Now, once it's dissolved, I now need to add something else to the mix. So I now need to do, in the second stage of this, I'm now going to add what's called my reference molecule. So the reference molecule is called TMS. Reference molecule is TMS. Now, you need to know what this stands. You need to know 3 things about this. Number 1, that it's called tetramethylsilane. Tetramethylsilane. You also need to know that its formula is Si brackets CH3 brackets 4. And you also need to know how to draw it. Si at the center, and you've got 4 CH3s. Anybody who knows me and has been watching my channel, I hate doing this short form. I like to draw them out properly. Notice that my bonds are very clearly going to my C's, by the way. So this is the reference molecule. Now, at this point, it's nice to mention everything about the reference molecule. So the reference molecule is used because TMS has a 0 chemical shift. TMS has that's actually the wrong way of phrasing it. Nothing, here's your bullet points. So the question would be, why TMS? So first bullet point I would always say is that nothing lies to the right of TMS. Cool. Hi, MA. Thanks for joining. It's clearly working then. That's awesome. Nothing lies to the right of TMS. Right of TMS. Next one is that it's non-toxic. That's always really useful. It's non-toxic. The next thing is it's easily removed. That's always a good one. It's easily removed. Easily removed. It also gives a strong single peak. Strong single peak in NMR in both C13 and proton NMR. So it has both. This makes TMS ideal for this circumstance And it's the reference molecule. It's got a chemical shift of 0. It's nice to add that onto the things to know about it. TMS, chem shift is 0 parts per million, 0 ppm. Yes, chemical shift is measured in ppm. I put this on the in my key terms. I just showed you every now and again that does crop up as a multiple choice question. What's the units for chemical shift? Anyway, moving on. So now that we've done this, we've added our reference. Now we can add it to our machine. And so this then goes into, this is how it works. I'm going to move down this section for me. So I'm not onto environments yet. I'm still on how it functions. So let's move this down way out the way, and I'll then pick up environments in a bit. So I'll move that down. Okay, so how does the machine work? Once you've got your sample, so now we're entering into this enormous, by the way, the machines are super cool. Number one is they're cooled to very low temperatures, using liquid nitrogen and sometimes even liquid helium. But actually, the reason why they're so cold is because we're using very powerful magnets. And here's how this works. You've now got your sample. You've got your sample dissolved in your solvent, and you've added TMS. What you now want to do is to place that into the machine. Now, when it's in the machine, the actual NMR machine, has enormous electromagnets, and I mean they are massive. And by the way, you shouldn't but don't ever use the word magnet or electromagnet. What you always mention in the exams is you need a strong magnetic field. So this is an electromagnet, and I'll put electromag. But in reality, more frequently the questions will ask you about the fact that what you need is a strong magnetic field. Yeah, so here's our powerful, super strong magnetic field. And we're going to put our sample inside it. Now, what I'm now going to do is I'm now going to pick up and start to explain to you regarding this around the actual nuclei of the atoms. So what I can now tell you is we're looking specifically now, guys, at C13. So what I'm going to do is I'm going to put a carbon-13 atom at the center of this. Now, at this point, students will commonly say to me, Mr. Duncan, but hang on a minute, we never talk about carbon-13 in our relative atomic masses. We're always about carbon-12, especially when you're working out things like MRs. So the first thing it's nice to note here, it's nice just to note that carbon-13 is approximately 1 in 1,000. So 1 in 1,000 carbon atoms is C13. Now, although that doesn't sound like a lot, it's actually a fairly substantial number, given that a mole contains 6.022 times 10 to the 23 atoms. You know, we have billions and billions and billions of atoms, and that means there are going to be plenty of C13s, and all the C12s now vanish, which is kind of cool. So along with this nota bene, we now need to do something rather strange, which is we need to make an enormous assumption. And the assumption here is that it's not even an assumption. I just need you to accept something. I need you to pretend that all carbon atoms in your substances in NMR are C13s. So if we were going to scan ethanol, we're going to scan ethanol in a C13 NMR. We are going to just blanket imagine that all carbons in it are C13s. Now, the reason for this is it doesn't actually, all the other ones that are not in that scenario simply overlay onto the graph, and they just kind of vanish into the mix. And what that means is, even though we get slight deviations on the peaks, it's one of the explanations why the peaks don't entirely line up and why the y-axis doesn't exist. But in reality, this is what I need you to do. Just accept. So when we're looking at, I've actually dissolved benzoic acid in this particular case. So I'm going to assume that every single C13 in this molecule, every carbon atom, are going to be C13s. That's the assumption you guys now have to make. So if you can do that for me, that would be ideal. So just pretend they're all C13s. So in the C13s, we learn about what's called nucleus spin. So the nucleus of an atom, nuclei of atoms, it's actually the nucleus in total, by the way. But what you imagine is that these nuclei have spin. So let's just do a C13. And this is going to spin. But what it's going to do is it is going to spin randomly. It's going to spin in a random orientation. I love how my laptop does that. It is spinning in a random way. Now, what we discovered was that if you now take that random spin and you put it into an immense, hugely powerful magnetic field, the spin will line up with the field. So the spin will line up. Now, what this does is it puts it into a particular energy state. Now, I can talk about the high-low energy states in terms of resonance, but you don't really need to know much about it. For those students who are looking to apply for universities to do chemistry, and you might have an interview with a university for a subject like chemistry, what I will tell you is that NMR is a very common interview question. And then you can add a little bit more detail into the two energy states of the spin. So what happens is you've got your C13 and you have a high energy spin state and a low energy spin state. And what happens is when you put it into a magnetic field, you align with a single one of these spin states. And then when you cause it to resonate, it will alternate between these two. But it's pure for those people who are interested. Go and have a look on ChemGuide. It gives a little bit more detail into the two spin states. You don't need it for A level. So here's what happens: the atom now lines up with the electromagnetic field. What I can now do, and by the way, yes, that question on the magnetic field does come up. The one that's actually more common, though, is what I'm about to do next. I'm going to change my pen to red. In order now to be able to detect these atoms, what I'm now going to do is I'm now going to hit it with radio waves. So I'm going to hit this with RF frequencies, RF waves, and radio frequency waves. Yeah, so this is RF. And those radio waves will cause certain atoms in certain environments to resonate. Now, what I'm now going to do is now that you've got this diagram, I'm just going to now make the diagram a little bit, I'm going to add in a second diagram here just to show you another version of this, to show you what I mean by the different environments. This is my first time mentioning ElecMag. Yeah, it's a strong magnetic field. And what I'm going to do is I'm going to put in our best friend ethanol, our Friday night molecule. And I'm going to make the assumption that all carbons are C13s. So let's add on my 13s here, the odd number of nucleons. And I'm now going to turn on my magnetic field. Yeah, my magnetic field comes in. I'm just going to show this as a very light set of lines like this. There's my mag field. And I'm going to line up the spin state of it. There we go. They both line up. Now what I'm going to do is I'm going to hit these with radio waves. Now what I'm going to do is I'm going to do two frequencies. I'm going to do a ping. Yeah. So my radio wave sounds like a ping, 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 ping. And you hear this, by the way, for those people who are interested, you can also look up the MRI machines work on this exact principle. So an MRI machine, that when you hear the clunk, 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 ding, 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 those are the radio frequencies that they're bombarding the molecules with. And I'm going to hit this with a ping. This is a radio frequency with a particular hertz, perhaps. And what this will do is this ping is going to create this. It's going to cause this one here to go into resonance. This is why it's called NMR, because it's nuclear magnetic resonance. This one here is now going to start to oscillate. It'll now all of a sudden go crazy. It'll start going nuts. It's actually technically moving between the two spin states. So it's actually alternating between these two spin states. So it's going backwards and forwards, between the two. And this now absorbs the ping. Now, what that means is I can then detect its absorption at that particular location. As long as my NMR machine is a three-dimensional machine rather than 2D, I can locate it. Yeah, that's the MRI machines for location. But in this case, I can actually measure the absorbent frequencies. Now, once I turn off the ping, once the ping is shut off, this one returns to its standard spin state, and it will stop, and it will go back to aligning itself with the field. I'm going to put that back on. Align itself back up with the field. What I'm now going to do is I'm now going to switch my frequency. So what I'm going to do, I'm now going to switch from a ping, I'm going to switch to a a dang. That's a good one. Dang, 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 dang. I'm going to change my frequency. And what that will now do is cause a different carbon-13 in a different environment to resonate. So this one starts now resonating between these two. It now goes crazy. And I can now pick up that one is different environments absorb different. This is the nota bene that goes along with this little stupid diagram. Nota bene. That's, by the way, for anyone who's new to the channel, that's for Latin for important notice. So nota bene. So this is different carbon-13s in different environments. Now, I'm using the word different environments. I can also put bracket non-equivalent. So the word equivalent means the same, right? Equal, equivalent. Non-equivalent means a different. So I'm going to then, so it's nice for me to add that word into there. Non-equivalent means different. Yeah, environments. And that does come up on exams, by the way. And you need to use it in your explanation, by the way. If they ask you to explain, I will actually, in my third lesson of this, I'll talk you through the process of building these in the exam question context. And you do have to use that term non-equivalent and equivalent environments. So C13s in different environments absorb, I shouldn't say absorb, I should say resonate with, but absorb's fine. Let's put resonate, why not? It's nice to use the word. Resonate with different frequencies. Diff frequencies of RF, radio frequencies, radio waves. Cool. I'll put that in a box. Love my spangly box. Make it spangly. Cool. So now that we've kind of got a basic idea about the processes involved, yeah, what I can now do, so I've now got to how the machine functions. What we can now do is start talking about our environment. So I can tick off my learning objective of how an NMR machine works. Now I need to talk to you about how we identify environments and what an environment is. So we've picked up several keywords here. We've picked up the equivalent and non-equivalent, meaning different and the same. We've picked up TMS, we've picked up deuterium, and we've talked about spin. Yeah, so this is the spin state. We talked about that before, spin state up here. Okay, so what we now need to do is we need to talk about an environment. So what I'm going to do now is I'm just going to give you the most basic concept of environments, and then we'll slowly step this up. So an environment of a carbon atom is actually based around two things. So I think most people here would agree. I'm going to once again go back to my favorite Friday night molecule of ethanol. We love ethanol. And the great thing is with NMR, you can do some lovely things with this. Again, we're sticking very, very clearly here with C13. Now, the first thing I want to point out here is that it's nice to have an idea about environments, that there is what is described as a maximum number. And the first thing I like to put down is nota bene, that the max number of environments is the total number of carbons, And this kind of makes sense. Like if I look at ethanol, I can't have three environments here. Yeah, that I have two carbons. The maximum number of environments I could have here is two. It's amazing how many people struggle and make simple errors like that. Yeah, they make simple mistakes where they count the wrong ones or whatever. It's nice just to have that as a basic kind of cap on how far we can go. So we need now to understand what each of the environments is. So let's now understand this. So what is an environment? An environment is so environments are built. So an environment is built from ... Number one, who you are connected to. Who you are connected to. Yeah, who you are connected to. ... So, for example, let's call this carbon atom A and this carbon atom B. If we look at the environment for A, we can say that A is connected to, so carbon A's environment, it is connected to 3 hydrogens and a carbon. So we've got 3 hydrogens and a carbon. So that is who carbon A is attached to. Yeah. The next, and by the way, I'll put that like this. There we go. It's attached to. So you don't really need to do that, but yeah, it's fine. So 3 hydrogens and 1 carbon. Right. The next part of your environment is your distance, and this is a common thing that's missed when teaching. It's the distance from electronegative atoms. Now, this is actually a little bit more complicated than that. You could actually just say, I like to actually say this, distance from anybody who's weird. I know that sounds odd, and in this case, the alcohol group is what makes this weird. So sometimes students like me to just give me a more clear description of this, and I'll show you what this means. This means that for carbon A, its distance from somebody weird, let's just call it oxygen, is going to be 2 moves. So this is 2 steps from O. Yeah. So if we now now that we have an understanding of this, we can kind of blend this process. You'd never write it down like this. This is purely for a teaching purpose. What you'd end up doing is I would usually just kind of go underneath it. You could argue that you would simply do something like this. I could do, this one is going to be 3 H's, a C, and 2 steps. Let's look at carbon B now. B is joined to 2 H's, a carbon, and an oxygen. That is not the same environment, and it is 1 step away from the oxygen. These are non-equivalent carbon-13s. They have different environments, which means I'm actually at my max number. There's going to be 2 environments. This process is super useful as a starting point of identifying environments. I'm giving you an actual kind of a total breakdown of what the environments are. In reality, by the time we get to the end of lesson 3, I'm going to hopefully have you not doing this anymore. Some students still like to do it, but you don't need to, because what we're going to be using is we're going to be using a term called symmetry in order to be able to use. Now, notice that symmetry is not in my keywords, but I like to add it on as an extra, because although you're not going to talk about symmetry in any of your A-level answers, symmetry is so useful for being able to quickly identify environments. I'll do a little bit of that now. Let's look at another example of this whole idea of concept of environments. So let's look at exam question number 1. So let's say I then give you this is I'm going to take my ethanol. I'm going to elongate it. Let's go for butan 1-ol. So how many environments would you now expect, based on the process I've just taught you, in carbon-13, how many environments do you think there would be? You can pause the video now and have a go at this and then forward your answer. So if you pause the video now, and then you can come back to it. Okay, so you should hopefully have had a go at this, and then you'll have got your answer. So the answer is the max number here would be 4. Max number of environments is 4. Do I have 4? So if I just take this as carbon number 1, I have got 3 H's, a carbon, and I am 1, 2, 3, 4 steps away from oxygen. So, that's so annoying the way it does that. 4 steps away from oxygen. My next one, I'm going to change my color for. This carbon has 2 H's. I'm going to stop writing them on now. 2 carbons, 1 on either side, and its distance is 1, 2, 3 steps away. I have to now go back to put that line back. My laptop does weird things sometimes. There we go. 3 steps away. Right. Next, what I'm going to do is I'm going to change my color again. Let's go for this carbon here. This carbon is 2 H's, 2 carbons, but is only 1, 2 steps away. Now, what I'm doing this one on purpose because students will commonly think that these 2 are in the same environment. They are not. The yellow carbon is far closer to the oxygen, which means it will be further downfield. Just to quickly give you an insight of this, we'll be doing data on this in a separate lesson. The NMR, we'll be doing NMR graphs, by the way, in the next lesson. This is chemical shift down here, chem shift in parts per million. And this here is TMS. There is technically no y-axis, by the way. And what's going to happen is the green carbon, this one here, this carbon here is going to be closer to TMS than the yellow one would. If I call this A, that's where A would be. And this one would be further downfield. Probably not a huge amount, by the way. The next one will be. B is going to be, let's call this one B here. And that's going to be further downfield. There's B. C, this one here is going to be much further downfield because it's closer to the electronegative oxygen. So the closer you are to somebody electronegative, the further shifted from zero you are. That's a really useful piece of information. So, okay, it's nice just to add this in. So this last carbon here at the end, which I will do in blue. Love my tablet. So this one is 2 H's, 1 carbon, an oxygen, and 1 step away. I have 4 different environments. So this process can be used. It's just quite long-winded. It can be used. And what I'm going to do to you now is to show you what symmetry is about. So question number 2, I'm now going to give you, and I'm going to try and add in as many opportunities to explore some A2 organic naming. So let's have a go at this one. So I'm going to draw this one out as question number 2 and see if you can pick up the number of environments. So first thing I'm going to do is I'm going to draw this out, and I'm going to ask you guys to have a go at naming this. So give me the A2 name for it. You can pause the video now, have a go at writing your own name, and then unpause it when you're ready. So the name of this one, number 1, it's got 4 carbons in it, so it's a bute. Yeah. And it's an ane. So bute comes from these carbons. I'm going to old school naming here. It's an ane because they're all carbon-carbon single bonds. Now, at AS level, if I cover up this guy, that's just butan 1-ol. But the problem is I now have a diol, and I need to include my numbers. Now, what I'm going to do is I'm going to do this. I'm going to change my color. So I've got this on carbon number 1 and this one on carbon number 4. So I'm going to leave a space here, and I'm going to go 1, 4, diol. Now, here's why I've left a space. This is why this is A2 naming, not AS naming. This is because if you have a di or tri suffix, then you will need to put the E back. This is to make sure that you don't have 2 consonants sitting next to each other. Yeah, you need to put the E back in. So this becomes butane with the E, 1,4-diol. So the question now now that we've had a go at doing a little bit of A2 naming, we can now have a go at how many environments they are. Now, what we could do here is I could do this the long way. I will do it the long way first, and then what I will do is I will then show you the short way. So carbon number 1 in green, and I'm going to go 1, 2, 3, and 4. Let's just have a look at these. So carbon number 1 is joined to 2 H's, a carbon, an oxygen, and is 1 step from that, but 1, 2, 3, 4 from that. So 2 numbers from the oxygens. Next, carbon number 2 is 2 H's. Sorry, my bonds has vanished. It's my tablet's fault. 2 H's, 2 C's. This is definitely different from the other guy. 2, it's not joined to an O at all. That's awesome. It's definitely different. And this is 1, 2 steps away. Darn it. 2 steps away from there. And 1, 2, 3 steps away from that one. Perfect. Let's go to the next guy. So the next guy, again, all my H bonds here vanishing. My next guy, number 3, is joined to 2 H's. It's joined to 2 C's. And it is 1, 2 steps away from that guy. And 1, 2, 3 steps away from that guy. Ooh. These are equivalent environments. They're equivalent. They're the same. What that means is they're not going to be separate peaks in the graph. So this one, let's do the last one. 2 H's, 1 C, 1 oxygen, and let's get rid of this line here, and 1 from him, and 1, 2, 3, 4 from him. Ooh, hello. I've got another set of equivalent hydrogens. Equiv environments. I am only, nice one, Mr. Duncan, environments. I'm only going to get 2 peaks in C13 here. Only 2 peaks. Yep. So at this point, I can now assign these. This is my graph going to be. So I've only got 2 environments. TMS is my reference molecule at 0 ppms on the chemical shift. Environment number 1, these guys are closest to the O. So I'm going to have a peak further shifted from 0, and I'm going to have an integration. This is the first time we're picking up the term integration, an integration of 2. Now, we can check our chemical shifts using our data book. I'm not going to do that in this lesson. There's not much time. But in terms of, I now pick up a new word, integration. Now, anybody who does A-level maths, integration is the area under the curve. Yeah, integration is the area under the peak. But in this case, this is this, and this is going to have an integration of 2. It's got an integration of 2 because there are 2 carbons in equivalent environments. What that means is I'm going to have another peak. It's going to be closer to 0. These 2 here are going to give me a second peak, because I've got 2 environments. And it's going to be closer to 0 because they're further away from electronegative oxygen. And their integration is going to be 2. It's exactly the same as the previous one. 2 carbons in the environment. Their integration ratio, commonly said, is going to be 2. They have the same integration. They commonly can use the integration to work out the number of carbons that are in environments. However, you do have to be aware that sometimes they give you it as a ratio, in which case you've then got to kind of do another little step in order to get to the actual whole number, but it's not very complicated. Okay, let's have a look at another case. Now, I've just told you that this is the hard way of doing it. What I'm now going to do is going to do the easy way, which is called symmetry. What I recognize here is that butane 1,4-diol is symmetrical. It has what's called a symmetry line. Now, just to tell you that there are 2 types of symmetry line in chemistry. You have molecular symmetry and you have partial symmetry. This one here has what's called a molecular symmetry line. Now, a molecular symmetry means a symmetry running through the entire molecule. Yeah, this is totally symmetrical through the whole thing. The other type of symmetry line is called a partial sim line, and I'll show you that. This is another nota bene. This is for symmetry. Yeah, symmetry. There are 2 types. We've got partial symmetry, partial sim, and molecular sim. And these are really useful to use, by the way. And spotting these will make your life so much easier. And I'm going to use them in a minute. Okay, so in this case, because they've got a symmetry line, what you can now do is count one side of the symmetry line. Because if they're symmetrical, the 2 are the same, they're equivalent. So what you do is, here's the rule. Find your symmetry lines and then count on or over the line. Rule, count carbons on or over the line. Brackets one side, lol. So I'm now going to go, I ignore one of the sides and I go, that's annoying. I ignore one of the sides. I have got 1, 2 environments here. I'm going to see 2 peaks. Symmetry lines are awesome. Let me show you another example of this. Okay, so let's go for this guy. I'm constantly surrounding, by the way, I'm kind of basing a lot of my things here off just a simple basic expansion on ethanol. So let's go for 2-methyl propan-2-ol. Gotta love it. Tertiary alcohol from AS level. Yeah. Okay. And what we can now do is we go, okay, I would like you to pause the video and give me the number of environments in C13, please. Off you go. Give me the number of environments in C13. This is question number 3. Okay, now the reason why I've chose this is because it has 2 partials. It has 3 partial sim lines. Yeah. The whole molecule, you can't split that in half like that. It doesn't really work. What we need to do is we realize that all 3 of these are the same. These are all equivalent. The symmetry is this with this, this with this. They're all exactly the same. Yeah. So now that I've picked out that these 3 are all the same, there's my first. I'm going to have an integration of 3, but this one, of course, will be different, and it will be far downfield because it's connected directly to the O. If you want it the long way, I can do a really quick version of the long way. If I do this one, this is 3 H's, 1 carbon, and 1, 2, 2 steps. This one here, I'll do a different color. This one here is 3 H's, 1 carbon, and 1, 2. It's the same. Yeah, this one here, I'm just giving a really quick run through. This one here is 3 H's, 1 carbon, and 1, 2. They're all exactly the same. So that's going to have an integration of 3, all equivalent. The one in the middle, though, is 3 carbons and oxygen and 1 step. So through 2 different environments, my graph for this TMS, you notice I always label TMS. I'm going to have 1 close to 0 with an integration of 3, and I'm going to have 1 slightly further down with an integration of 1. Nice to see how this is done. Now, at this point, most people will probably feel like, oh, I kind of see what's going on here. I want to give you a better example of a partial sim line. I'm not a particular fan of the one I just did. I'm going to go for a better example of a partial sim line. If you want to pause this and have a go at naming it, all the rest are H's. If you want to have a go at naming this, all the rest are H's. I'll be good since I'm doing an online webinar. I'll be good. I'm coming to the end of my lesson now, by the way. We're just getting to grips with symmetries and environments of C13s. So what's interesting is there's no molecular sim line here. I can't do that. But there is a partial sim line. Yet the partial symmetry line is here. These two are the same. So at that point, because there's no other symmetries, I can simply count my environments as 1, 2, 3, 4, and then 5. These two are the same. So I'm going to have 5 things purely because if there's no symmetry at all, you max it out at your max number of carbons. But if there's symmetry, you can then reduce the number. I'll give you another one. So this had 5 environments. I'm questioning to see how many of you guys are getting right now. Let's try another one, just one that's interesting. Everyone hates benzene at A-level chemistry, which is hilarious. So if I now add on, let's do benzoic acid. I'm going to draw that a little bit better. Let's do benzoic acid. That's a fun one. We mentioned it earlier in the lesson because we used a polar solvent for it. Here's our benzoic acid. So how many environments do you think there would be? You can pause it. So do I have Masaru? Hey, Masaru, I used to teach years ago. Nice to see you, Masaru. How are you getting on, dude? You okay? Send me a nice message on the chat. I don't know what year Masaru will be in now. AS or A2? I don't know, Masaru. Oh, it's good to see you. How many will it be? Pause the video, have a go at it. Now, this one's a nice one because it does have a symmetry line. It has a symmetry line here. Yeah. Now, lots of people will go, Mr. Duncan, I don't like that because this isn't the same as this. I totally get it. So what you could argue here is that there's a partial sim line if you prefer it this way. You could just do there's a partial sim line there. We know that all of these are carbons. Count on and over the line. So I'm going to have 1, 2, 3, 4, 5. Yeah. To give you a bit more, I just finished my first year of the University of Toronto. For real. That's amazing, Masaru. It's so nice to see you. Oh, dude. What are you studying? Let me know. So this is going to have 5. If I now I can start doing fun games with this. There's 5 in this one. The integrations of these would be, so the carbon labeled number 1 would have an integration of 1. The carbon labeled number 2 will have an integration of 2. The carbon labeled number 3 will have an integration of 2. And the carbon label number 4 will have an integration of 1. And the carbon number 5 is going to have an integration of 1. It's kind of nice to see that. Yeah, computer science and maths. That's awesome, dude. I'm so glad you're doing so well. University of Toronto. That's awesome. I lived in Toronto for a year and I absolutely loved it. I hope you're enjoying it. I used to live at Bloor and Spadina so many years ago. Our street dogs on Bloor and Spadina are excellent. Also, go to the Little Italy's awesome. Love Little Italy. Anyway, nice to talk about this, folks. Nice to catch up with old students. So anyway, I'm going to leave you there, I think. Let's go back to my learning objectives. It's nice just to have done. We've talked about identifying environments, and we're working towards our key terms, which is awesome. We've talked about chemical shift a little bit, but we will do a little bit more of that next lesson. And we'll link it to the data booklet. Guys, I hope you found it a useful lesson. I do have a couple of exam questions here to look at, but I think at the moment, I think it's worthwhile me picking those exam questions up next time. I'm going to turn my camera back on. I'll stop sharing my screen. It's been a 15-minute lesson. I hope you guys find it useful. If you don't, and by the way, for all those people who aren't really onto my videos or don't really like them, I'm sorry if they're not perfect. I do my very best. I'm just a lowly teacher trying to help out students out there with their chemistry. I hope you found it useful. I'll see you tomorrow for part 2. Catch you later, everybody.